Hi, my name is Brian Caffo, and this is the lecture on likelihood in the Statistical Inference Coursera class. This is part of our data science series, and this is co-taught with my co-instructors, Roger Peng and Jeff Leek. We're all in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. So it would be hard to think of a more central topic to statistical inference than the likelihood. And the likelihood is a technique that by and large corresponds to when you have a fully specified statistical model. And so, let's talk about this. So a common and fruitful approach to statistics is to assume that the data arises from a family of distributions indexed by a parameter that represents a useful summary of the data. So for example, we might assume that our data x1 to xn arise from a normal distribution indexed by two parameters, right? The mean and the variance. So that's an example of doing that. So the likelihood, which we foreshadowed a little bit in other lectures, is the joint density of the data evaluated as a function of the parameters with the data fixed. And so we'll go through an example. So the likelihood is a central topic in all aspects of statistical inference, but there is a way in which you can directly use the likelihood to perform inference regarding the unknown parameter. So the likelihood, here's our definition. Given a statistical probability mass function or density, f of x theta, where theta is an unknown parameter, the likelihood is f viewed as a function of theta for fixed observed value of x. So what usually happens is we assume, say, x1 up to xn are, let's say, IID from some distribution f, and that, or density f, or mass function f, and that mass function depends on a parameter theta. So the likelihood of theta given the data x, let me just write x with a little underscore underneath it to denote the full data set, is, and I'm going to write this symbol to mean proportional to the product I equal 1 to n f of xi and theta. And the product, we take the product here because the data is independent. The likelihood, I say proportional to here rather than equal to. We could just write equal to, but it's important to think of the likelihood as not something that has an absolute scale. Its only interpretation really is in the relative scale. So you can compare, likelihood for theta 1 and x over likelihood for theta 2 and x. That's meaningful, but you can't say that likelihood for theta 1 by itself is a terribly meaningful quantity. It's only relative to another hypothesized value of the parameter. So that's the likelihood, and that's how we usually generate it. We usually have, for the purposes of this class, we're always going to have IID data, so we just take products of the density or mass function. So you can directly use, so the likelihood tells us about a lot of, underlies a lot of different theories of statistics. So as an example, Bayesian statistics is the likelihood is a central quantity in Bayesian statistics. In frequency statistics, the likelihood guarantees things about certain kinds of hypothesis tests via some very famous old theorems. And then in likelihood analysis, people just directly use the likelihood for analyses. And so I'm going to talk a little bit about that. And basically, likelihood analysis uses ratios of likelihood values. And there's kind of an interesting old paper that tries to come up with the idea of, given a model, what constitutes evidence. And if you buy into that kind of philosophy literature, then likelihood ratios measure relative evidence of one value of the unknown parameter to another. And then there's this interesting paper by Birnbaum that says that given a statistical model and observed data, all of the relevant information contained in the data regarding the unknown parameter is contained in the likelihood. That's a very controversial old result by a person named Birnbaum that has sort of been talked about for decades since he first introduced it. And if you have a bunch of which is kind of most germane to us, if you have a bunch of independent random variables, their likelihoods multiply. Okay. So let's go through an example, because I think it's probably very abstract for people right now, and it's a little hard to follow. I think with an example it'll be very clear. Suppose we flip a coin with success probability theta, so it's a potentially biased coin. And then recall that the mass function for theta is this guy right here, where x is either 0 tails or 1 heads. So this should not come as news to anyone. Suppose that the result is a head. Remember, a likelihood, we have to have the data in hand to create the likelihood. Okay, so the likelihood is, and then I'm going to write the likelihood, corresponding to the value of 1, which we observed, right? It's going to be theta to the 1, 1 minus theta to the 1 minus 1, which is theta, for theta in 0 to 1. So therefore, our likelihood for the 0.5 for a fair coin relative to the likelihood that the coin is unfair with a success probability of a quarter, quarter being 1/4, not the unit of currency quarter, is 2, right? Because what this is equal to theta 1 over theta 2, right? Because our likelihood is just theta. In this case, it's 0.5 or 0.25, okay? And so we would interpret this, if you're buying into the likelihood way of thinking about things, there's twice as much evidence supporting the hypothesis that the coin is fair to the hypothesis that the coin is unfair in the specific way of having a 25% chance as a head. And then you can compare any two possible values of theta, and the likelihood will spit back the relative evidence supporting either of those. Okay, now let's just modify the problem a little bit, and suppose now we flip our coin 4 times and we get the sequence 1, 0, 1, 1. Okay? So the likelihood, and I'm going to write it in this kind of weird way, the likelihood of theta, then given the data 1, 0, 1, 1, is going to be the part of the likelihood corresponding to the first one, the part of the likelihood corresponding to the second flip, which was a 0, the part of the likelihood corresponding to the third flip, which was a 1, and the part of the likelihood which is corresponding to the fourth flip, which is also a 1. Combine all these terms and you get theta to the 3, 1 minus theta to the 1. It's interesting to note, I think hopefully you can catch this at this point, that the likelihood only depends on the total number of heads and the total number of tails. So we might just write this as likelihood 1, 3 for the total one tail and 3 heads. Okay? And that's also a little bit weird notation, but I'm doing that just to remind us. It's also important to note that this idea that we don't need the full data set, we just need the total number of heads and the sample size, or the total number of heads and total number of tails, to specify the likelihood. And there's this concept called sufficiency, which says that the total number of heads is sufficient. It's sufficient to know them to know the likelihood, under the knowledge that the Bernoulli model and the IID model are correct. Okay. So now our likelihood for 0.5, comparing our likelihood to 0.25, right? Comparing a fair coin to an unfair coin in a specific way, is 0.5 cubed, 1 minus 0.5, divided by 0.25 cubed, 1 minus 0.25, right? And that works out to be about 5.33. So now we can interpret this as there's over 5 times as much evidence supporting the hypothesis that theta equals 5 over the hypothesis that theta equals 0.25. So that's how you do likelihood style analysis. It gets much harder as the models get more complicated. But this gives you an idea of what's going on. And obviously, a fair coin is a particularly useful interest in this problem. But in general, you want to know. You don't want just 2 values, you want to compare kind of all values. So the obvious thing to do would be to consider all values between 0 and 1. And a likelihood plot just displays the parameter by the likelihood. But remember, likelihoods are relative values, right? So if you get a likelihood that looks like this, right, it only makes sense to compare theta 1 to theta 2, right? It only makes sense to compare the ratio of those heights. So L of theta 2, L of theta 1. But notice if we divide the likelihood by a constant, right, then L of theta 2 over that constant divided by L of theta 1 divided by that constant, then that's going to just be equal to the ratio. Okay? And so, it's nice to kind of normalize our likelihood so we can look at them across problems. And so why don't we normalize it so its height is 1? Well, that's what's interesting about that is the way to do that is to find the point theta hat for which the likelihood achieves its maximum. That's called the maximum likelihood estimate. Okay? There's the point where the likelihood receives its maximum. And so instead of plotting the likelihood, right, we could plot the likelihood of theta divided by the likelihood of theta hat. And that will peak out at 1 at the point theta hat. Here it is for our sequence of zeros and 1 values from our coin experiment. The likelihood does exactly what you want. So in this case, if you get 3 heads and out of 4 coin flips, the MLE, the point at which this achieves its maximum, is at the point P equal theta hat equal to 3/4. Okay, so here I've got a kind of a sequence of values of P. Well, I renamed it instead of theta, I'm calling it P. Here's my sequence of values of P that I'd like to, the grid that I'd like to plot my function on. And then the likelihood I would just be saying 3 successes out of 4 trials where I'm viewing my function as a function of the parameter, so I'm evaluating it at 1,000 values of P to plot my function. But then I divide it by the instance where it achieves its maximum at 3/4, right? And so we get this function right here, and notice it peaks out at 1, and then notice, of course, this function is going to be maximized at 0.75 at the MLE. Now, so the MLE is the best supported point given the data. Think about the MLE for a second. It makes a lot of sense, right? It's the value of the parameter that makes the data that we observed most probable. So it has this really nice interpretation. But the likelihood does exactly what we would like. We would like it to be, to suggest that yes, 0.75 is a well-supported value of the parameter, but 0.73 is a pretty well-supported value of the parameter as well. But 0.3, over here is not a very well-supported version of the parameter. And the likelihood is wide because we only have 4 coin flips. And what would happen is as we get more coin flips, the likelihood is going to get more and more peaked around its MLE. Okay, so let's just discuss maximum likelihood a little bit more. The value of theta where the curve reaches its maximum is the so-called maximum likelihood estimator. So it is the value of the parameter that is most well supported by the data given the likelihood. So it's called the maximum likelihood estimator, or MLE. So we could just define the MLE as the argument maximum of the likelihood over theta. And it has this nice interpretation that the MLE is the value of the parameter that makes the data that we observed most probable, right? So the likelihood is kind of thinking of the joint probability of the data as a function of the parameter. So it's sort of like tuning that parameter to where it makes the probability that we observe the probability of the data that we observed most probable, which seems to make sense because we did observe the data that we observed, so it must be somewhat probable. So here's some results. If we have some normal data, IID normal data, the MLE of mu is x bar, and the MLE of sigma squared is the bias sample variance, where you divide by n instead of n minus 1. If x1 to xn are Bernoulli, then the MLE of p is x bar, the sample proportion of 1s. If xi are binomial, ni, pi, then the MLE of p is the total proportion of 1s. Okay? If the x's are Poisson lambda t, if an x is Poisson lambda t, then the MLE of lambda is x over t, the rate. If you have a bunch of IID Poisson random variables, then the MLE of lambda is the total number of events divided by the total rate. Okay? So let's go through this example right here, where you saw 5 failure events for 94 days of monitoring a nuclear pump. Assuming a Poisson model, plot the likelihood. And by the way, right, we know what the MLE is, right? The MLE is 5 over 94. Okay? Let's see. So my lambda is the parameter I'm interested in. So I'm just going to create a grid of lambda values to create my function. My likelihood is just the Poisson density, now viewed as a function of all these lambda parameters, but remembering that in each case I sampled for 94 days with the data fixed at 5. And then the MLE for lambda, lambda hat, is equal to 5 over 94. So 94 times lambda hat is just 5. So if I plug in 5 for lambda, I will get the MLE. Okay. I will get the likelihood at the MLE. So if I plot my lambda by my likelihood, and then I don't like the frame around it, line width is 3, type equals L connects it in a line, and my x, so if you type expression, it'll actually put the symbol lambda rather than the word lambda. So you can be fancy like that if you'd like. And then here's this red line is just showing where the MLE is, and then of course the likelihood achieves 1 at that point. And then I draw these two kind of reference lines. I'll talk about them in a second. Okay, so this is the likelihood. So this is a plot of the estimated rate by the evidential support for that estimated rate. So if we wanted to compare, this point and this point, it would be that ratio of those two guys. Okay. Now, I like to draw these reference lines for the following reasons. So this reference line is at 1/8, and this reference line is at 1/16. Okay? And the reason I like to draw these reference lines is as follows. This point, so I know that this line is 1/8 right here. So take this value of lambda right there and compare it to the MLE value of lambda, right? This ratio, because the top is 1 and the bottom is 1/8, that ratio is 8 if you put the MLE in the numerator, and 1/8 if you put this value in the numerator. And the same thing would go for this value right here at that corner. So basically, the MLE is 8 times better supported than that point. But then if I take any other point in between the two, right, its height, because its height is a little bit less than the MLE, we know that it's going to be slightly less well supported, and so that it'll be slightly less than 8 times better supported. Okay. But what's interesting, right? If you were to take now, remember this is 1/8 right here. Take this point right here, right? Okay. That value of lambda, right? Its value is less than 1/8, So when we were to compare it to the MLE, it would be worse than 8 times better support. The MLE would be better than 8 times supported than that point. Okay, so any other point in this range, right? You cannot find a point that's more than 8 times better supported, right? Every point outside of that range, you can find a point that's more than 8 times better supported. So these collection of points right here, these collection of lambda values right here, are exactly the points such that there is no other point that is more than 8 times better supported, if we draw that line at 1/8. Of course, this is all predicated at having normalized the likelihood with the MLE at 1. And this line right here, all of the points of lambda that fall within this interval, right, because it's 1/16, are the points such that there is no point that is more than 16 times better supported, okay? And that's kind of useful, right? Because you can do these experiments. So where do I get 8 and 16? So 8 is 2 cubed and 16 is 2 to the 4th. I get those because if you do these coin flipping experiments where comparing the likelihood of whether a coin is two-headed versus the likelihood of the coin being fair, you find that kind of intuitively people start switching. If they get 3 consecutive heads, they start saying, oh, that coin appears to be unfair, to the tune of being two-headed. And at about 4 consecutive coin flips, they're quite certain that the coin is unfair. So, I consider these kind of like moderate and sort of strong evidence in favor of the points within these line. So just to reiterate, if you take this interval, it's kind of like these are basically the likelihood equivalent of a confidence interval. And so if you take all of these points, there is no such point that is more than 8 times better supported given the data in the model. If you take a point outside of it, say this point, we know at least one point, namely the MLE, that's more than 8 times better supported. So those are little so-called likelihood intervals. And you might say, well, wait, the 1/8 is kind of arbitrary, but it's no more or less arbitrary than, say, constructing a 95% confidence interval. What you really want to give people is the full plot, because it conveys all of the relevant information. The only problem with likelihood is if you have multiple parameters, like in a regression setting, then you have to figure out how to do something that displays just the likelihood. But I wanted everyone to at least hear about the likelihood. The remainder of the class will be focusing more on kind of frequency style inference that does not show likelihood-based plots, but I wanted people to be aware of this style of inference.